So this video will cover section 5.3, which is on types of reactions. So the majority of chemical reactions fall into these categories: combination, decomposition, single replacement, and double replacement. So these first four types of reactions are telling you how, so it tells you if you have one or two reactant and a product, or the reverse, then you know it's a combination or a decomposition. And if you have a compound and an element and you obtain a different compound and an element, you know it's a single replacement. And double replacements are when ions typically exchange partners. So it's more about how atoms behave, how they, combine or uncombined. So then we will learn about combustion reactions, which are a subtype of oxidation reductions, and this will be covered in section 5.4. And we'll learn about acid-base reactions in chapter 9. But you have to realize that acid-base reactions and precipitation reactions, for example, are double replacement reactions. And we will also see that oxidation-reduction reactions are typically single replacement reactions, among others. So let's go over those first four types: combination, decomposition, single replacement, and double replacement. So a combination reaction is the joining of two or more reactants to form a single product. So the key to recognize a combination reaction is to see that you have two reactants and only one product. So those two reactants will combine to make a bigger molecule, if you will. For example, when we have magnesium being burned in oxygen, so you have magnesium and oxygen as reactant, and you're forming the magnesium oxide, one product. If you are synthesizing an ammonia from nitrogen and hydrogen, the bottom equation there, you will combine them and form the ammonia gas. And that's also a combination reaction because you have only one product. Decomposition reactions are the conversion of a single reactant to two or more products. So it's really the opposite process of a combination. In this, you start with one reactant and it decomposes into two or more products. So the key is to see that you have one reactant and then on the other side of the arrow, two or more products. Let's look at the examples here. We have mercury oxide here being decomposed. And so typically those decomposition reactions, they require energy to happen or heat. And here the delta symbol represents heat. You need heat to decompose the mercury oxide into mercury liquid. Mercury is the only metal that is liquid at room temperature. And you can retrieve oxygen gas. So from one reactant, you obtain two products. Another decomposition reaction below, the potassium chlorate can be decomposed using heat to bring back KCl and 3 oxygen gas molecules. So decompositions are really the opposite of combination reactions. They have only one reactant and form two or more products. Now, single replacement reactions. It's a reaction in which one element replaces another element in a compound to form a different compound and element as products. So if we look at the generic form here, we start with element A and we add to it the compound BC. And the C will combine with the element A and form a new compound AC. and then B will be by itself. So you see that we started with an element and a compound, and we obtain a different element and a different compound. There has been an exchange of element. The compound has exchanged partner. So in the examples here, so zinc plus 2 HCl gives zinc chloride plus the hydrogen gas. So you see that on the left, zinc is an element, it's by itself, and HCl is the compound. And so the compound will switch and get rid of the hydrogen and take on the zinc. So now the compound is zinc chloride, and the hydrogen is an element. H2 gas is an element because it's just hydrogen atoms, and so that makes it an element. So we have a different element and a different compound. So if we look at the second example, we see the same feature where we have Fe is iron as an element, combining with a compound of copper sulfate. So the copper sulfate, the sulfate will drop the copper and take on the iron. And so on the right side, now you have iron sulfate, and the copper is by itself. So now copper is the element and the iron sulfate is the compound. And so these single replacement reactions are typically oxidation-reduction reactions. You don't see it here, but there has been a transfer of electrons from an element to another. And that's what characterizes oxidation-reduction reactions. Now, double replacement reactions. There are reactions in which two compounds exchange parts, so atoms or ions, to form two new compounds. So you recognize the double replacement reactions by the fact that you start with two different compounds and you end up with two completely new products, which are two compounds as well. So in the generic form of the double replacement reaction, where you have AB plus CD, so that represents two compounds made of two, 4 different kinds of atoms there. And they will exchange partner. A will combine with D, and then C will combine with B. And so now you have a new compound AD and another new compound CB. So that's how you recognize the double replacement reaction. If we look at the examples, the first example, silver nitrate plus sodium chloride gives silver chloride and sodium nitrate. So here you can maybe see that silver is no more with the nitrate, it combined with the chloride ion. So Ag combined with Cl to make a new compound. And then the Na will combine with the NO3 to make a new compound. In the second example, we also see that we have two compounds to start with. And so the NaOH, the sodium from NaOH will combine with the chloride from HCl to form NaCl. And then the hydrogens from HCl will combine with the OH minus from the NaOH, and H plus OH makes HOH, which is actually water, right? So it happens to be an acid-base reaction. This second example, NaOH is a base, HCl is an acid, and they're forming a salt plus water. And that's very characteristic of acid-base reactions. So this is an example of an acid-base reaction, and it shows you how it is a double replacement reaction. And the example above was actually a precipitation reaction, where you have two solutions of two ionic compounds, and they exchange partner. And when they exchange partner, one of the new compound formed is AgCl is a solid, and all the other compounds are aqueous solutions. And so that solid, the AgCl, will be seen as a white cloud forming into solution, and that's a powder, and powders are solid, and that's what we call a precipitate. So precipitation reactions are double replacement reactions. So let's practice watching how atoms behave in reactions and identify each reaction as a combination. The capital C will symbolize combination. Decomposition, symbolized by D. Single replacement, SR, and double replacement as DR. So let's look at the first example. And again, as always, I want you to pause the video to work this out on your own before you watch the answer. So the first example, 3Ba solid plus N2 gas gives Ba3N2 solid. So this can be seen as a combination reaction. And the key to recognize that is that there is only one product. One product, so that tells you it's a combination reaction. Second example, 2Ag solid plus H2S aqueous gives Ag2S solid plus hydrogen gas. So here, if we look carefully, we start with an element. Ag is an element, it's by itself, and H2S is a compound. And then we see that Ag is taking the place of hydrogen to make a sulfide compound of Ag2S. And then the hydrogens are free and making the diatomic molecule hydrogen gas, which is an element. So we are going from an element plus a compound and making a new compound and a new element. And so that's typical of a single replacement reaction. Third example, SiO2 solid plus 4HF aqueous gives SiF4 solid plus 2 H2O liquid. So here we can see that we start with two different compounds and we end up with two new compounds. So we can probably find that there is a double replacement here. If we look at SiO2, it becomes SiF4. So there has been an exchange from oxide to fluorine. And if you look at HF, HF now it has become H2O. So the hydrogen is no more with the fluorine, but now with the oxygen. So there has been an exchange of a double replacement reaction. So this is a double replacement reaction where they've exchanged partners. So fourth example, with K2CO3 solid gives K2O aqueous plus CO2 gas. Here we see there is only one reactant and then two products. So that's key to recognize a decomposition reaction, right? One reactant being decomposed into two or more products. Next example, we have 3 magnesium solid plus 2 iron chloride and gives 3 MgCl2 plus 2 Fe. So if we look carefully, we can see on the left side that we have magnesium by itself, so that's an element. Then we have a compound of iron and chlorine. And on the other side, we have magnesium with chlorine making a compound and iron by itself. So we started with an element and a compound, and the compound changed its structure by taking the magnesium in and leaving the iron out. So now we have a new compound and a different element. So that's a single replacement reaction. Last example, CO2 plus H2O gives H2CO3. Here we see we have only one product, and so that's key to recognize a combination reaction. Here we are synthesizing carbonic acid. So let's learn more about combustion reactions. We've talked about combustion reactions already. We've seen examples of them. And combustions is synonymous to burning. And in combustion reaction, a carbon-containing compound, and that's the fuel, will burn in the presence of oxygen. And oxygen comes from the air, and its formula is O2. And it will produce carbon dioxide, CO2, and water, H2O. And it will produce a lot of heat and a flame, typically. So these are what we call exothermic reactions. They release a lot of energy, and that is the reason why we use them a lot. We take advantage of those combustion reactions for all kinds of energy needs. Because the carbon-containing compound, the fuel, can be anything like methane and butane in those examples, but it can be wood, wax, kerosene, gasoline, all the fossil fuels that we are using to get energy from, coal. So all of these are molecules made of carbon and hydrogens and oxygen. And when you burn them with oxygen from the air, you always will make carbon dioxide and water and release a lot of energy. And that's why we use them a lot. And so you can see that they have the delta above the arrow, which says you need a spark typically to start the reaction. And then after that, it goes very easily and releases a lot of heat. Methane is a natural gas, and so we use that to cook and heat our houses. So that's how the energy is being used. Butane is also used, it's also a gas that we burn, and we use the energy to cook or to do other things where we need energy. So combustion reactions are a subtype of oxidation-reduction reactions, and we will cover these in the next section.